This is the story of how the largest ecosystem on Earth is slowly suffocating, and most people have no idea it's happening. Since 1960, the ocean has lost roughly 2% of its dissolved oxygen. That number sounds small until you translate it into weight. About 77 billion metric tons of oxygen gone from the water. Completely oxygen-free zones in the ocean have quadrupled in volume during that same period. Coastal sites, reporting dangerously low oxygen levels, have jumped from just 45 in the 1960s to around 700 today. And what makes this worse is that our best computer models can only reproduce about a third of the oxygen loss we've actually measured, which tells us the real situation is almost certainly outpacing our projections. This is ocean deoxygenation. It ranks among the most consequential environmental crises unfolding right now, and by the end of this video, you will understand exactly why scientists are calling it a wake-up call for humanity. We're going to cover the science behind it, the places it's already devastating, the billions of dollars it's costing, its connection to the worst mass die-off in Earth's history, and what, if anything, can still be done about it. We'll start with the basics, because most people don't realize something about the air they breathe. The ocean produces at least 50% of all the oxygen on Earth. That figure comes from NOAA, NASA, and the Woods Hole Oceanographic Institution. Some estimates push as high as 70 to 80%, though the most authoritative sources land on at least half. Either way, every other breath you take exists because the ocean made it. Microscopic organisms called phytoplankton do the heavy lifting here. These tiny, floating, photosynthetic creatures live in the sunlit upper layer of the ocean, roughly the top 200 meters, and they generate oxygen through photosynthesis, the same way plants on land do. One species in particular, a cyanobacterium called Prochlorococcus, cranks out up to 20% of all the oxygen in the entire biosphere, which is more than all the tropical rainforests on the planet combined. Another group, the diatoms, contributes roughly another 20% on top of that. So the ocean functions as a massive oxygen factory. But here's the catch. Nearly all the oxygen produced by marine life also gets consumed by marine life through respiration and decomposition. Fish breathe it, bacteria burn through it, while breaking down dead organic matter as it sinks through the water column, and the ocean's net contribution to our atmospheric oxygen supply ends up being relatively small on short timescales. The real issue here isn't about our air supply. It's about what happens to the creatures living in the water. Oxygen enters the ocean two ways. First, it dissolves from the atmosphere at the sea surface, where wind and waves help mix it in. Second, phytoplankton photosynthesis produces it directly in the upper ocean. But below the sunlit zone, everything changes. No photosynthesis happens down there, which means no new oxygen gets created. Everything below about 200 meters depends entirely on oxygen that formed or dissolved above and then traveled downward. That downward transport relies on a process called thermohaline circulation. Cold, dense, oxygen-rich water at the poles sinks and creeps along the ocean floor, eventually delivering oxygen to the deep. This process operates on timescales of roughly 1,000 years. Hold on to that number, because we're going to come back to it. So the picture looks like this. Oxygen enters the ocean at the surface and the poles and gets consumed everywhere else. That's the baseline. And what happens when you warm the planet is that three things go wrong at once, all of them draining oxygen from the water. The first one comes down to pure physics. Warmer water holds less dissolved gas. If you've ever noticed that a warm soda goes flat faster than a cold one, you've seen this principle play out. As the ocean warms, its capacity to hold oxygen drops. A landmark 2017 study, published in Nature by Sönke Schmidtko and colleagues at the Geomar Helmholtz Center for Ocean Research in Germany, pinned this temperature-driven solubility change at approximately 15% of the total ocean oxygen loss and about 50% of the loss in the upper 1,000 meters. But that only accounts for a fraction of the problem. The second mechanism cuts deeper. When the ocean's surface warms, it becomes lighter and more buoyant compared to the colder, denser water below, creating what scientists call increased stratification. Picture a warm cap sitting on top of cold water. That cap blocks surface and deep waters from mixing, and since the surface is where the oxygen lives, less of it gets transported downward. The deep ocean essentially gets cut off from its oxygen supply. The third mechanism works through biology. Warmer water speeds up metabolic rates in marine organisms, which means they breathe faster and burn through more oxygen. Warming also accelerates microbial decomposition, which consumes oxygen too. So you end up with less oxygen arriving in the deep ocean and more oxygen being consumed by the life already down there. It's a squeeze from both directions. These three forces working in tandem, reduced solubility, increased stratification, and ramped up metabolic demand, drive what scientists call open ocean deoxygenation. And climate change sits at the center of all of it. But a second, parallel crisis has been building in coastal waters, and it runs on a different engine. Coastal deoxygenation traces back to nutrient pollution. Excess nitrogen and phosphorus from agriculture, sewage, and industrial runoff flow into rivers, which carry them straight to the coast. Those nutrients act as fertilizer for the ocean, triggering massive blooms of algae at the surface. When the algae die, they sink to the bottom, and bacteria devour enormous amounts of oxygen, breaking them down. Once oxygen levels fall low enough, you get hypoxia, dangerously low oxygen. When they hit zero, that's anoxia, a complete absence of oxygen. These low oxygen and no oxygen zones carry a name that is not an exaggeration: dead zones. Inside a dead zone, most complex marine life cannot survive. Fish flee if they can. Bottom-dwelling organisms that have nowhere to go simply die where they sit. What remains is a stretch of ocean floor that looks like an underwater graveyard. Researchers off the Oregon coast filmed once vibrant reefs turned completely lifeless after oxygen levels crashed. So, two parallel processes are draining oxygen from the ocean. In the open ocean, climate change warms the water, caps it with a buoyant layer, and starves the deep of oxygen. In coastal waters, nutrient pollution feeds algal blooms that consume oxygen as they decompose. And climate change amplifies the coastal problem too, layering warming on top of the nutrient damage. Together, these two drivers have produced an oxygen crisis that is larger, faster, and more far-reaching than most people realize. Now for the hard numbers. The most complete global measurement of ocean oxygen loss came from that 2017 Nature study by Schmidtko, Strama, and Visbeck at GeoMar. After analyzing over 50 years of ocean data, they found the global ocean had shed approximately 2% of its dissolved oxygen since 1960, a decline of about 4.8 petamoles, give or take 2.1. Limburg and colleagues in Frontiers in Ecology and the Environment expressed that differently. Roughly 77 billion metric tons. North Pacific waters showed the greatest losses. 3/4 of the total oxygen decline occurred below 1,200 meters depth, which is the hardest layer to fix, because deep ocean circulation takes roughly 1,000 years to complete a full cycle. A machine learning follow-up using the BLENDAR framework, developed at Georgia Tech, confirmed a loss rate of about 0.7% per decade between 1970 and 2010. And a 2025 extension of that analysis turned up something new and alarming: severely accelerated oxygen loss in the Arctic Ocean and North Atlantic over the past decade, faster than anyone had previously estimated. Meanwhile, completely anoxic water, water with zero oxygen, has quadrupled in volume since the 1960s. Open ocean areas with very low oxygen have expanded by more than 4.5 million square kilometers at 200 meters depth since 1960. To give that scale, It's an area larger than the entire European Union. And here's the number that should unsettle everyone. Earth system models, the sophisticated computer simulations used to project future climate change, reproduced only about 1/3 of the observed oxygen loss, roughly 0.6% versus the observed 2%. Andreas Oschlies at Geomar put it plainly: they are not able to reproduce the recent oxygen decline exactly. Instead, they significantly underestimate the observed oxygen loss. That gap means our future projections are almost certainly conservative. The real trajectory is likely running ahead of what the models show. The growth in dead zones alone tells a staggering story. Scientists documented about 4 worldwide in the 1910s. By the 1960s, that count reached around 45. Robert Diaz and Rutger Rosenberg tallied 305 by 1995. And by the time they published their landmark science paper in August 2008, the number had surpassed 400, covering a combined area of more than 245,000 square kilometers. By 2019, the IUCN reported approximately 700 sites worldwide with low oxygen conditions. Robert Diaz, a professor at the Virginia Institute of Marine Science, summed up the trend in a line that still holds. Dead zones were once rare, now they're commonplace. There are more of them in more places. That same 2008 paper contained what has become one of the most cited sentences in this field. Diaz and Rosenberg wrote, "There is no other variable of such ecological importance to coastal marine ecosystems that has changed so drastically over such a short time as dissolved oxygen. Dead zones have spread exponentially since the 1960s, roughly doubling each decade, and not all of them are the same size. The biggest ones stretch across areas that are almost impossible to picture. Sitting in the Gulf of Oman and the broader Arabian Sea is the largest dead zone on Earth. In 2018, researchers led by Bastian Quest at the University of East Anglia confirmed its scale at approximately 165,000 square kilometers, roughly the size of Florida. With an oxygen minimum zone about 1,000 meters thick, Quest described his findings with 3 words that became a headline: "The ocean is suffocating." The Baltic Sea hosts the largest human-caused dead zone, covering roughly 70,000 square kilometers, an area about the size of Ireland. 7 of the world's 10 largest dead zones sit in the Baltic, and the situation feeds on itself through a vicious cycle. When bottom waters lose oxygen, phosphorus escapes from the sediments, which stimulates cyanobacteria growth at the surface. Those cyanobacteria die and sink. Their decomposition burns through more oxygen, which releases more phosphorus. That self-sustaining loop makes recovery extraordinarily difficult, even when nutrient inputs drop. Another massive zone sits in the Bay of Bengal at roughly 60,000 square kilometers, between 100 and 400 meters depth. A 2016 study by Bristow and colleagues in Nature Geoscience found it teetering at a tipping point of becoming fully anoxic, and more than 400 million people live around the Bay of Bengal's rim. Between 1973 and the late 1980s, the Black Sea dead zone ballooned from about 3,500 square kilometers to roughly 40,000. And then there's the dead zone that draws the most attention in the United States, the one in the Gulf of Mexico. Every summer, it forms on the Texas-Louisiana shelf, fed by nutrient runoff carried down the Mississippi River from farms across the Midwest. Researcher Nancy Rabelais at Louisiana State University and LUMCON began systematically measuring it in 1985, and the surveys have continued every year since. Summer 2017 produced the largest Gulf dead zone on record at 22,730 square kilometers, or 8,776 square miles, roughly the size of New Jersey. The 2024 measurement came in at 17,365 square kilometers, or 6,000 705 square miles, making it the 12th largest in 38 years. In 2025, it measured about 11,400 square kilometers, or 4,402 square miles, below the long-term average. But here's the thing. The 5-year average remains more than double the target set by the Hypoxia Task Force, a state and federal partnership formed in 1997 with the goal of shrinking the dead zone to less than 1,900 square miles by 2035. They are nowhere close. The Gulf's commercial and recreational fishing industry generates $57 billion in economic impact and supports 200,000 jobs, according to NOAA. 40% of the nation's seafood comes from the Gulf. When the dead zone expands, it doesn't just kill marine life, it reshapes entire economies. A 2020 report by the Union of Concerned Scientists, authored by Rebecca Boehm and titled Reviving the Dead Zone, pegged the annual damage at $2.4 billion to fisheries and marine habitat. The record-setting 2017 dead zone cut brown shrimp habitat by 25%. A separate study covering 1999 to 2005 found that the North Carolina shrimp fishery alone hemorrhaged 12.9% of its annual catch, amounting to $1.25 million per year. From Hypoxia, one fishery, one state. Fixing the problem carries its own price tag. A 2025 study by researchers at West Virginia University, Iowa State, and the University of Texas, funded by the National Science Foundation, calculated that reaching the EPA's 45% nitrogen reduction goal would cost approximately $7 billion per year. And the Gulf of Mexico is just one dead zone. Multiply those kinds of economic impacts across 700 sites worldwide, and the scale starts to come into focus. The damage extends well beyond American waters. Baltic Sea cod landings dropped from approximately 50,000 tons in 2010 to less than a third of that by 2018, and the loss of bottom-dwelling organisms in the Baltic represents a deficit of 106,000 metric tons of fish food annually, according to reporting from EOS and the American Geophysical Union. Tuna and billfish habitat in the northeastern tropical Atlantic shrank by 15% from 1960 to 2010 as expanding oxygen minimum zones compressed their livable space. And global tuna fishing generates approximately $42 billion annually. South Korea tallied $300 million in damages from a single jellyfish bloom that thrived in deoxygenated conditions. In 1998, a nutrient-driven red tide wiped out 90% of Hong Kong's fish farm stock, a $40 million loss in one event. The IUCN, in its landmark 2019 report, acknowledged the limits of what we know. Much remains unknown as to the long-term human health, social and economic consequences of ocean oxygen loss. The numbers we have are likely an undercount, because deoxygenation impacts tangle with the related effects of warming and acidification in ways that are hard to separate. And that connection matters because ocean deoxygenation doesn't exist on its own. It belongs to what scientists have named the deadly trio. In 2013, the International Programme on the State of the Ocean, or IPSO, along with the IUCN, published their State of the Ocean report and introduced that term. All three members of the trio trace back to the same root cause: human-generated carbon dioxide emissions. Ocean warming comes first. Since 1970, the ocean has absorbed over 90% of the excess heat trapped by greenhouse gases, acting as a buffer that keeps the atmosphere from heating even faster. But that absorbed heat is fundamentally changing the water. Ocean acidification comes second. Roughly 30% of the carbon dioxide humans have emitted has been absorbed by the ocean, where it reacts with seawater to form carbonic acid. The ocean's pH has dropped by about 0.1 units, and because pH operates on a logarithmic scale, That 0.1 shift translates to a 30% increase in acidity. Ocean deoxygenation is the third. These three stresses don't just coexist, they amplify each other. Warming drives deoxygenation through reduced solubility and increased stratification. Respiration simultaneously consumes oxygen and releases CO2, creating localized acidification. And deoxygenated waters produce greenhouse gases, including nitrous oxide, a gas with approximately 300 times the warming potential of CO2 and methane. Up to 30% of atmospheric nitrous oxide emissions come from the ocean, and oxygen minimum zones contribute more than half of that total. So deoxygenation doesn't just result from climate change, it accelerates it. The warmer the ocean gets, the less oxygen it holds, and the less oxygen it holds, the more greenhouse gases it produces, which drives further warming. It's a loop that feeds itself. Dan Lafferty, the IUCN's senior advisor on marine science and conservation, described the situation at the release of the IUCN's 2019 report at COP25 in Madrid. We are now seeing increasingly low levels of dissolved oxygen across large areas of the open ocean. This is perhaps the ultimate wake-up call from the uncontrolled experiment humanity is unleashing on the world's ocean as carbon emissions continue to increase. Everything covered so far might make this sound like an unprecedented situation. In terms of speed, it is. But the basic mechanism, warm oceans losing oxygen and life dying as a result, has played out before. And the last time it happened on a truly global scale, it very nearly ended all complex life on Earth. That story is next. A long time ago, something nearly wiped life off the face of the Earth. Scientists call it the Permian-Triassic extinction, though it earned a more fitting name, the Great Dying. 81% of all marine species were killed. Not 81% of individuals, 81% of species. For a long time, the exact cause stayed unclear. Flooding, sudden climate shift, volcanic catastrophe, all of them were candidates. But over the past 2 decades, a much sharper picture has emerged from rock chemistry, isotope ratios, and fossil records spanning multiple continents. And that picture looks uncomfortably familiar. The trigger was volcanism. The Siberian Traps, one of the largest volcanic events in Earth's history, erupted across what is now northern Russia and buried an area roughly the size of Western Europe in lava. But the lava wasn't the real killer. The carbon dioxide was. Trillions of tons of CO2 flooded into the atmosphere over tens of thousands of years, which triggered extreme greenhouse warming, which heated the oceans, which drained the oceans of their oxygen. And none of it happened overnight. This detail matters. Research, published in Nature Communications, Earth and Environment in 2024, found that ocean deoxygenation started approximately 900,000 years before the main extinction pulse. It was the many thousands of years of oxygen slowly, steadily leaking out of the water before the system crossed a threshold and collapsed catastrophically. The oceans didn't just lose oxygen, they became what geochemists call euxinic, meaning they were both oxygen-starved and saturated with hydrogen sulfide, a toxic gas produced by anaerobic sulfate-reducing bacteria that flourish in the total absence of oxygen. Hydrogen sulfide gives rotten eggs their smell. It is acutely toxic to most complex life. And in the Permian oceans, it was being generated on an almost incomprehensible scale. A hypothesis proposed by Kump, Pavlov, and Arthur in 2005 suggests that this hydrogen sulfide didn't stay in the water. As concentrations climbed beyond what the ocean could contain, the gas bubbled out and rose into the atmosphere in massive quantities, poisoning terrestrial life directly and shredding the ozone layer, the thin shield protecting life from the sun's ultraviolet radiation. With the ozone gone, surviving organisms on land absorbed lethal doses of UV. The ocean didn't just kill what lived in the water. It reached up and killed what lived on the land and under the sky. What followed was a planet-wide toxic gas chamber that exported its poison to every surface of the Earth. it is difficult to overstate how total the devastation was. Recovery took centuries, and millennia later, let that number settle. Research from Stanford University, published in the Proceedings of the National Academy of Sciences in 2016, confirmed that life didn't rebound until ocean anoxia had fully ebbed. The oxygen had to return before life could return. For years, the ocean stayed too oxygen poor to support complex ecosystems. And this is where it stops being a paleontology lesson and becomes something far more urgent. In 2022, Justin Penn and Curtis Deutsch, researchers at Princeton and the University of Washington, published a study in Science that drew a direct line between the Permian extinction and our current trajectory. They built models mapping how rising temperatures and falling oxygen would affect marine biodiversity across the globe, then compared those projections to the fossil record of the Great Dying. The patterns matched. The same types of species in the same types of environments showed the same vulnerabilities. Their conclusion landed hard. If greenhouse gas emissions continue unabated, Earth would be on course for an end Permian-level mass extinction by approximately the year 2300. A few centuries within the potential lifespan of civilizations that already exist today. Cold water species near the poles would suffer the worst losses because those organisms are specially designed for oxygen-rich environments and have nowhere left to migrate. The poles are already the coldest places on Earth. When those waters warm and lose oxygen, no cooler or more oxygen-rich refuge exists. Tropical species at least carry some biological tolerance for lower oxygen levels. Polar species carry none. For them, deoxygenation is a dead end in the most literal sense. To be absolutely clear, because accuracy matters, we are not currently in a Permian-level extinction. The parallel is about trajectory, not current state. We have not crossed the point of no return. But the mechanism is identical. Carbon dioxide floods the atmosphere, the ocean warms, oxygen vanishes, life dies. The only difference is the source of the carbon. In the ancient world, it came from the Siberian traps. Today it comes from power plants, automobiles, deforestation, and industrial agriculture. The geological process that nearly ended all complex life is being replicated by human industry, only faster. The Permian-Triassic extinction is the most dramatic example, but the geological record holds multiple instances where ocean oxygen loss coincided with catastrophic biodiversity collapse. Two of them carry lessons that land especially close to home. The late Devonian extinction may have been set off by something almost poetic in its irony. Researchers, including Thomas Algeo at the University of Cincinnati, have proposed that the spread of the first vast forests was the catalyst. The culprit were possibly the trees. The very organisms we associate with life and oxygen and environmental health may have caused one of the worst mass extinctions in history. As forests spread across continents for the first time, their deep root systems weathered rocks on a scale that had never occurred before, releasing phosphorus into rivers. That phosphorus washed into the ocean, acted as a massive pulse of fertilizer, and triggered enormous algal blooms. When those algae died and sank, bacteria consumed vast amounts of oxygen, breaking them down, and the oceans suffocated. The process mirrors exactly what creates coastal dead zones today. Agricultural fertilizer washes off farmland, enters rivers, flows to the coast, feeds algal blooms, and spawns oxygen-depleted zones. The late Devonian version was just the first time it played out. And if the hypothesis holds, the late Devonian extinction stands as the only mass extinction in Earth's history with a biological trigger rather than a geological one. No asteroid, no mega eruption, no sudden cosmic event, just life itself reshaping the planet's chemistry in ways that turned the ocean deadly. The parallel to humanity's current role, flooding the ocean with nutrients from industrial agriculture and carbon dioxide from fossil fuel combustion, is impossible to miss. One more example deserves attention: and in many ways it unsettles more than any of the others, precisely because of how little it took. The Silurian Kozlowski extinction rarely appears in documentaries, and most people have never heard of it. But research from Florida State University, published in the journal Geology in 2019, uncovered a detail that should give every scientist and policymaker pause. 8%. That's all it took. Only 8% of the ocean needed to lose its oxygen to drive this extinction event. Not the whole ocean, not even most of it, not 50%, not 20%. And what makes this finding so directly relevant to today is that the extinction had no known catastrophic trigger, no asteroid impact, no massive volcanic eruption, no single dramatic event anyone can point to. The researchers specifically noted that it was one of the few extinction events comparable to the large-scale declines in biodiversity currently happening today. An unremarkable, gradual shift in ocean oxygen, affecting a relatively small fraction of the total ocean volume, killed enough life to register in the fossil record a vast span of geological time later. The message is hard to overstate. Global anoxia is not the threshold for catastrophe. Hollywood-scale disaster is not the requirement. You just need enough oxygen to disappear from enough of the right places. And that is precisely what is happening right now, in our ocean, on our watch. So what does ocean deoxygenation actually do to the creatures living in the water today? The effects run far deeper and wider than the simple idea that fish can't breathe. The damage cascades through every level of the marine food web, from the behavior of individual organisms to the architecture of entire ecosystems. One of the most insidious consequences goes by the name habitat compression. As oxygen minimum zones expand and rise toward the surface, the band of water carrying enough dissolved oxygen to support complex life gets squeezed into an ever narrower layer near the top. Fish, squid, tuna, billfish, sharks, and every other species that needs substantial oxygen to fuel an active metabolism gets forced upward into this shrinking slice of livable ocean. Their three-dimensional habitat is being flattened from below. Between 1960 and 2010, researchers documented that the oxygenated upper ocean layer in the tropical northeastern Atlantic was shrinking at approximately 1 meter per year. 1 meter per year, every year, for 50 years straight, adding up to roughly a 15% reduction in available habitat for species like tuna and billfish, some of the most economically valuable fish in the world. And this compression creates a perverse secondary effect that directly hits the fishing industry. When fish crowd into a narrower band near the surface, they become more concentrated, easier to locate with sonar, and easier to catch with nets and long lines. Fishing fleets targeting these compressed populations can actually see their short-term catch rates climb, even as the underlying population shrinks and weakens. It creates an illusion of abundance. Deoxygenation makes overfishing easier and more likely at exactly the moment when fish populations are under the most biological stress and least able to absorb additional pressure. The toll on individual fish is severe and well documented. Under low oxygen conditions, fish ramp up their gill ventilation rates, pumping up to 5 times more water across their gills in a desperate attempt to extract enough oxygen. That effort is enormously energy-intensive and diverts biological resources away from growth, reproduction, immune function, and predator avoidance. Studies have recorded growth rate declines of 20 to 30% in fish exposed to chronic low oxygen, and fish in hypoxic waters end up smaller, weaker, and less healthy than their counterparts in well-oxygenated environments. Vision deteriorates too, which is a less obvious but serious consequence. Photoreceptor tissues in the eyes rank among the most oxygen-hungry tissues in a fish's body, requiring a constant high supply to function. When dissolved oxygen in the surrounding water runs scarce, vision degrades, sometimes severely, making it harder to find food, spot predators, and navigate complex environments like coral reefs or rocky outcrops. Research published in the Philosophical Transactions of the Royal Society specifically flagged the physiological and ecological implications of deoxygenation for marine vision, calling it an underappreciated but potentially critical impact pathway. Reproduction suffers as well. Low oxygen triggers hormonal imbalances, slashes egg production in females, and causes developmental abnormalities in embryos and larvae. Even if adult fish manage to survive a low oxygen zone, the next generation may arrive in reduced numbers, in poor health, or not at all. That means the impacts of a deoxygenation event can propagate forward in time, suppressing populations for years or decades after the oxygen itself has returned. A 2025 study published in Nature Communications, Earth and Environment provided a vivid window into what extended deoxygenation does to entire fish communities over longer timescales. Researchers examined Mediterranean sediment cores and found that during a deoxygenation event thousands of years ago, mesopelagic fish, the species inhabiting middle depths between about 200 and 1,000 meters, nearly vanished from the record. Surface-dwelling species like anchovy replaced them, surviving in the remaining thin, oxygenated layer near the top. The entire vertical structure of the fish community collapsed into a narrow band. When reoxygenation eventually began, total fish abundance tripled. The ecosystem bounced back, but only after the oxygen came back first. Same lesson as the Permian, playing out on a smaller stage and a shorter clock. Recovery follows reoxygenation, not the other way around. Bottom-dwelling organisms arguably take the hardest hit of all. Unlike pelagic fish that can at least attempt to swim away, many benthic organisms are sessile or slow-moving. Crabs, clams, worms, sea cucumbers, sponges, and the countless creatures forming the foundation of seafloor ecosystems are essentially trapped when oxygen levels crash. When dissolved oxygen drops below their survival threshold, they die in place. Mass mortality events among bottom fauna have been documented repeatedly in the Gulf of Mexico, the Baltic Sea, the Black Sea, and off the Oregon coast, with footage showing seafloors carpeted in dead organisms that had no escape route. And those dead creatures on the seafloor don't just vanish. Their decomposition, powered by bacteria that consume oxygen, pulls dissolved oxygen levels down even further, creating a feedback loop that deepens and prolongs dead zone events well beyond what the original trigger would have caused alone. Death generates more death. Each mass mortality event makes the next one more likely and more severe. But one group of organisms doesn't just survive in low oxygen water, it positively thrives, and its rise stands as one of the most visible signs that something has gone deeply wrong in the ocean. Jellyfish. They lack brains, hearts, and bones. They count among the most ancient animal groups on Earth, with a body plan that has remained essentially unchanged since well before the age of fish and terrestrial creatures. And their simplicity, the fact that they amount to little more than gelatinous sacks of water with stinging tentacles, turns out to be an extraordinary survival advantage in a deoxygenating ocean. They tolerate oxygen levels that would kill most fish and persist in conditions that are essentially uninhabitable for their competitors and predators. In the Gulf of Mexico and the Baltic Sea, jellyfish have been documented moving into dead zones and replacing the fish populations that used to live there. Where shrimp and cod and commercially valuable species once thrived, swarms of jellyfish now pulse through water that nothing else can survive in. This represents something more than an ecological curiosity. Scientists sometimes describe it as the ocean transitioning from a fish-based ecosystem to a jellyfish-based ecosystem, and the implications cascade outward through every connected industry and community. Jellyfish are not a useful food source for most commercially valuable fish. They don't support the same food chains, and they don't generate the same economic value. An ocean dominated by jellyfish produces far less of the protein that billions of people worldwide depend on, And jellyfish don't just passively benefit from the crisis, they actively worsen it through multiple channels. They consume fish, eggs, and larvae, directly undercutting the ability of fish populations to recover even when oxygen conditions improve. Their metabolic waste favors microbial food webs over the more complex food chains that sustain global fisheries. And when jellyfish die in large numbers, their decomposition consumes oxygen from the surrounding water in exactly the same way decomposing algal blooms do. Deoxygenation favors jellyfish, and jellyfish, through their feeding, their waste, and their death, favor more deoxygenation. It's another self-reinforcing loop in a crisis that generates them at every turn. Japan offers the most dramatic real-world example. Starting in the early 2000s, annual blooms of Nomura's jellyfish began appearing in Japanese waters. These are not the small, translucent creatures most people picture. Nomura's jellyfish grow up to 6 feet across and weigh 200 kilograms, roughly 440 pounds, with a single individual larger than a person. Blooms of this species used to occur about once every 40 years, rare enough that a fisherman might see one in a lifetime. But starting around 2002, they showed up every single year. The impact on Japanese fishing communities was devastating. Nomura's jellyfish clogged fishing nets, tore them apart with sheer weight, rendered catches useless, invaded fish farms, smothered stock, drove up costs, and drove down revenues for operations already running on thin margins. One swarm actually capsized an entire fishing trawler, and the crew had to be rescued from the water. South Korea estimated damages from a single jellyfish bloom at approximately $300 million. These are not projections. They are real losses that have already hit real communities, and as dead zones continue to expand, the conditions fueling these blooms spread with them. Now for one of the most dramatic real-world examples of what ocean deoxygenation looks like when it arrives somewhere it has never been before, with no warning and no obvious local cause. In 2002, dead zones appeared off the coast of Oregon for the first time in over 50 years of continuous scientific observation. Marine scientists who had studied the Oregon shelf for decades had never recorded anything like it. And unlike the Gulf of Mexico or the Baltic Sea, where the link between agricultural runoff and oxygen depletion is well established, the Oregon dead zones had nothing to do with local pollution. No massive farming operations sat upstream. No sewage outfall poisoned the water. The cause was something far harder to fix. Natural ocean upwelling gone wrong because of climate change. Upwelling normally works as a benefit along the Pacific coast. Prevailing winds push surface water offshore, and cold, nutrient-rich water from the deep rises to replace it, feeding the incredibly productive ecosystems of the Pacific Northwest and supporting world-class fisheries for salmon, Dungeness crab, and dozens of other commercially valuable species. But climate change altered the equation. Wind patterns along the coast became more persistent, driving stronger and more prolonged upwelling events that pulled more deep water to the surface for longer stretches. And the deep water coming up was already oxygen depleted, because expanding oxygen minimum zones driven by climate change throughout the open Pacific had crept closer to the continental shelf. Oregon got hit from both directions at once. Stronger upwelling brought more deep water to the coast than normal, and that deep water carried less oxygen than it used to because of global-scale deoxygenation happening thousands of miles away. Local conditions and planetary trends converged into a crisis nobody saw coming. By 2006, the situation escalated dramatically. For the first time ever recorded in those waters, oxygen dropped to absolute zero. True anoxia, complete absence of dissolved oxygen. The water was biologically dead. Underwater footage from Oregon State University showed once vibrant rocky reefs turned lifeless. Rockfish gone, crabs gone, sea anemones gone. Everything that couldn't swim away fast enough had simply died. And what makes the Oregon story so critically important is that these dead zones have formed every single summer since 2002. Not occasionally, not only during unusual weather years, but every year without exception for more than 2 decades. Oregon researchers now say the state has a hypoxia season, the same way it has a fire season, a permanent, recurring feature of their coastal environment materialized from nowhere in just a few years. Driven not by anything Oregonians did locally, but by global climate change, reshaping ocean circulation patterns across the entire Pacific Basin. Francis Chan and Jack Barth at Oregon State University have led the investigation of this phenomenon since its discovery, and their work carries a message that reaches far beyond Oregon. Even pristine coastlines, thousands of miles from major agricultural operations, are vulnerable to deoxygenation through the indirect effects of climate change on ocean circulation. Any region where deep water regularly rises to the surface, the west coasts of North America, South America, and Africa, faces the same potential risk. Deeper in the ocean, in zones where oxygen has always run naturally low, conditions are getting critically worse. Oxygen minimum zones, or OMZs, are persistent layers of very low oxygen, sitting at roughly 200 to 1,500 meters depth, primarily along the western coasts of continents. They form naturally, where biological consumption of oxygen from decomposing organic matter, sinking from above, exceeds the supply delivered by deep ocean currents. They've existed as a normal feature of ocean chemistry for as long as scientists have studied them. But they are expanding. Since 1960, open ocean areas with very low oxygen have grown by more than 4.5 million square kilometers at 200 meters depth. According to Strama and colleagues, an area roughly the size of the European Union, shifting from adequately oxygenated to dangerously depleted in just 6 decades. In January 2023, Princeton researchers led by Busek and Resplandy published findings that the Pacific Ocean's massive oxygen minimum zone is growing, with projections suggesting it could expand by up to 8 million cubic kilometers by century's end. Their research also resolved a 15-year debate in the modeling community by showing that while the outer boundary of the OMZ expands and threatens ecosystems at its edges, the OMZ core, where oxygen sits at its absolute lowest, may actually contract. The answer turns out to be both at once, depending on where you look. But the expansion of the outer boundaries is what matters most for marine life, because that's where livable habitat is being eroded, and organisms are being compressed upward and squeezed out of waters they've inhabited for generations. NOAA describes oxygen minimum zones as forming where surface biological productivity runs high, biological oxygen consumption at depth runs high, and water circulation moves sluggishly. Climate change is amplifying all 3 of those conditions simultaneously. There is also a dimension of the crisis that rarely gets the attention it deserves, and it ties straight back to climate change in a way that closes a dangerous loop. Low oxygen waters don't just sit passively. They actively generate greenhouse gases. When oxygen levels drop far enough, microbial communities in the water switch to different metabolic pathways. Instead of using oxygen to decompose organic matter, they use nitrogen compounds and produce nitrous oxide, known as N2O, as a byproduct. Nitrous oxide carries approximately 300 times the warming potential of carbon dioxide. Up to 30% of all atmospheric nitrous oxide emissions come from the ocean, and oxygen minimum zones contribute more than half of that total. Baltic Sea dead zones are also producing methane from their sediments, another potent greenhouse gas that can rise through the water column and enter the atmosphere. So the full feedback loop looks like this. Human sea up there, the released phosphorus fertilizes cyanobacteria, the blue-green algae that form massive blooms across the Baltic every summer. Those cyanobacteria grow explosively, and when they die, they sink. Bacteria on the seafloor decompose them, burning through enormous amounts of oxygen. Oxygen drops further, which frees even more phosphorus from the sediments, which feeds more cyanobacteria, which die and consume more oxygen. dead zones create the conditions for more dead zones, and the Baltic has been stuck in this loop for decades. Even aggressive nutrient reduction under the HELCOM Baltic Sea Action Plan, adopted in 2007 across 9 Baltic nations, has produced painfully slow progress because internal phosphorus recycling from the dead zones themselves keeps feeding the problem from below, even as external inputs shrink from above. That self-perpetuating quality is one of the reasons scientists worry so much about letting deoxygenation advance. Beyond a certain threshold, the system builds its own momentum, and breaking the cycle requires not just stopping the inputs that started it, but actively overcoming the internal feedbacks now perpetuating it. The projections for where this is heading come from the most authoritative source available, the IPCC. In September 2019, the IPCC released its special report on the ocean and cryosphere in a changing climate, known as the SROCC, projecting a 3 to 4% decline in ocean oxygen by 2100 under high emissions scenarios, with oxygen loss emerging over 59 to 80% of the ocean area by 2031 to 2050. Then in 2022, the IPCC AR6 Working Group 2 report updated those numbers using more advanced CMIP6 models, and the picture got significantly worse. For the subsurface ocean between 100 and 600 meters depth, relative to a 1995 to 2014 baseline, the projected losses break down like this. About 4.1% under the strong mitigation scenario, SSP 126. About 6.6% under the moderate SSP 245. About 10.1% under high emissions, SSP 370, and approximately 11.2% under the worst-case SSP 585. These CMIP6 projections run 31 to 72% higher than the earlier CMIP5 estimates. Better models, worse outlook. By 2080, approximately 70% of the world's oceans could be losing oxygen at unnatural rates, according to Long and colleagues in Geophysical Research Letters in 2022. Their work identified 2021 as the year that significant mesopelagic deoxygenation officially emerged from the background noise of natural variability as a statistically detectable, human-driven trend. But the most sobering number belongs to Andreas Oschlies at GeoMar, published in Nature Communications in 2021. He calculated that even if CO2 emissions stopped immediately, today, right now, the deep ocean would still lose more than 10% of its pre-industrial oxygen content over the coming centuries. Less than 25% of this committed oxygen loss has already played out. The rest is locked in by warming that has already occurred, and the decline is projected to continue for 1,000 years or more. That 1,000-year timescale of deep ocean circulation from earlier in this video, this is where it becomes terrifyingly relevant. Heat, already added to the ocean surface, will take centuries to fully penetrate the deep, and as it does, it will keep driving oxygen loss long after the last ton of carbon has been emitted. Even in the best-case scenario, the deep ocean will be losing oxygen for generations we will never meet. The IUCN put it in plain language in its 2019 report summary. What is reported here, and in the full technical report, is probably an underestimation of what is happening now. Science is incomplete, and broader awareness of ocean deoxygenation is just happening, but what is already known is very worrying. Behind every one of those statistics, behind every one of those studies, actual people have spent their careers trying to understand this crisis, raise the alarm, and push a largely indifferent world to act before it's too late. And for most of the history of oceanography, these researchers worked in almost total obscurity. Ocean deoxygenation didn't carry a name the public recognized. No movement stood behind it. No Al Gore or Greta Thunberg turned it into a dinner table conversation. It lacked the visual drama of a bleaching coral reef or a polar bear stranded on shrinking ice. You can't photograph oxygen that isn't there, and you can't film the absence of something dissolved in water. The very invisibility of the crisis made it nearly impossible to communicate beyond the lab. For decades, the people studying ocean oxygen loss published papers that almost nobody outside their narrow field read. They presented data at conferences to rooms full of specialists who already grasped the gravity of the situation, while the rest of the world stayed completely unaware. That frustration, knowing something catastrophic is unfolding and being unable to get anyone outside your discipline to pay attention, has shaped the way many of these scientists communicate today. An urgency runs through their public statements that goes beyond normal academic caution, because they understand that the gap between what the science shows and what the public knows is itself a form of danger. That dynamic has started to shift, slowly, particularly since 2017 and 2018, when several landmark studies and reports dragged ocean deoxygenation into mainstream scientific discussion. But public awareness still falls far below what the severity of the crisis warrants. Understanding who these people are, what they've discovered, and what institutional infrastructure they've assembled matters, because that infrastructure will determine whether the world responds to this crisis effectively or keeps sleepwalking toward consequences that will last for centuries. If one study brought ocean deoxygenation into the global scientific spotlight, it's the paper published in Science on the 5th of January 2018 by Denise Breitberg and colleagues. Breitberg is a marine ecologist at the Smithsonian Environmental Research Center in Maryland, who served as co-chair of GO2NE, the Global Ocean Oxygen Network, and led what became the definitive review of declining oxygen in both the open ocean and coastal waters. That paper, with its finding that anoxic water volume had quadrupled and that roughly 700 coastal sites now reported low oxygen conditions, synthesized decades of fragmented research into a single, unified picture for the first time. Breitberg articulated the stakes in terms that cut through the academic jargon. "Oxygen is fundamental to life in the oceans," she stated in the press release accompanying the paper. "The decline in ocean oxygen ranks among the most serious effects of human activities on the Earth's environment." But she also offered something too many environmental stories leave out: a note of agency. "This is a problem we can solve," she added. "Halting climate change requires a global effort, but even local actions can help with nutrient-driven oxygen decline." That framing, acknowledging severity while refusing to surrender to despair, has been a consistent thread running through Breitberg's public communications. The 2018 paper came out of GO2NE with dozens of co-authors, and several of those co-authors deserve individual recognition for the scale of their contributions. Lisa Levin, Distinguished Professor Emerita at the Scripps Institution of Oceanography at UC San Diego, has spent decades studying the deep ocean, with a particular focus on oxygen minimum zones and the organisms inhabiting them. She contributed to both the IPCC Special Report on the Ocean and Cryosphere in a Changing Climate, released in September 2019, and the IPCC's Sixth Assessment Report. The Aslo Redfield Lifetime Achievement Award came in 2018, followed by the Prince Albert I Grand Medal in Ocean Science in 2019, and election to the National Academy of Sciences in 2024. Her career arc traces the growing recognition that ocean deoxygenation is not a niche concern but a first-order threat to the planet. Levin has been especially effective at communicating the economic dimensions. Commenting on the Breitberg paper in January 2018, she put it this way: "It's a tremendous loss to all the support services that rely on recreation and tourism, hotels and restaurants and taxi drivers and everything else. The reverberations of unhealthy ecosystems in the ocean can be extensive." That observation captures something that often gets missed. Oxygen loss in the ocean doesn't stay in the ocean. It ripples outward through coastal economies, food systems, and livelihoods that seem distant from the sea but depend on it entirely. Andreas Oschlies, a professor at the Geomar Helmholtz Center for Ocean Research in Kiel, Germany, stands as arguably the single most important figure in the institutional effort to coordinate global research on this problem. He leads the Global Ocean Oxygen Decade, known as GOOD, an official program of the United Nations Decade of Ocean Science for Sustainable Development, running from 2021 to 2030. He authored Chapter 3.1 of the IUCN's landmark 2019 report, organized the 2018 Ocean Deoxygenation Conference in Kiel, that brought together more than 300 scientists from 33 countries and co-authored the 2024 paper proposing aquatic deoxygenation as a 10th planetary boundary. Oshleys published the deeply sobering finding in Nature Communications in 2021 that even if carbon dioxide emissions stopped immediately, the deep ocean would still shed more than 10% of its pre-industrial oxygen over the coming centuries. He has also been one of the most candid voices about the limitations of current models. After publishing a paper in Nature Geoscience in June 2018, showing that models significantly underestimate observed oxygen loss, Oshleys stated flatly, "They are not able to reproduce the recent oxygen decline exactly. Instead, they significantly underestimate the observed oxygen loss." That kind of intellectual honesty, naming what the science doesn't know as clearly as what it does, keeps credibility intact in a field where the stakes run high and the temptation to either overstate or understate the problem never goes away. Robert Diaz at the Virginia Institute of Marine Science, part of the College of William and Mary, bears more responsibility than anyone for documenting the global proliferation of dead zones. His work, with Rutger Rosenberg, culminating in their August 2008 science paper, produced the first comprehensive global inventory of coastal dead zones and remains the most cited reference point in the field. Diaz tracked the growth from 4 documented dead zones in the 1910s to more than 400 by 2008. Dead zones were once rare, he put it. Now they're commonplace. There are more of them in more places. Simple, direct, and impossible to misread. Sunke Schmidtko, also at Geomar, led the 2017 Nature paper that first comprehensively quantified global ocean oxygen loss at approximately 2% since 1960. That study delivered the foundational statistic that now appears in virtually every discussion of ocean deoxygenation. Without Schmidtko's painstaking analysis of more than 50 years of ocean data, the field would still lack a clear, defensible number for how much oxygen the ocean has lost. Lothar Stramer, another Geomar researcher, pioneered early documentation of expanding tropical oxygen minimum zones, publishing key findings in Science in 2008, showing these zones were growing in every tropical ocean basin. He also captured the asymmetry of the crisis in a single observation. While the slight decrease of oxygen in the atmosphere is currently considered non-critical, the oxygen losses in the ocean can have far-reaching consequences because of the uneven distribution. The atmosphere mixes relatively quickly. The ocean does not. Oxygen loss in the ocean is patchy, concentrated, and devastating precisely because it isn't evenly spread. Nancy Rabale at Louisiana State University and LUMCON has served as the principal investigator for the annual Gulf of Mexico Dead Zone surveys since she began systematic measurements in 1985. Nearly 4 decades of continuous monitoring by one researcher and her team, building the longest and most detailed record of any dead zone on Earth. Without Rabelais' work, the Gulf Dead Zone would be far less understood, far less documented, and far less likely to receive the scientific and political attention it has drawn. Justin Penn and Curtis Deutsch, the Princeton and University of Washington researchers, whose 2022 science paper drew the direct line between current emissions and Permian-level extinction by 2300, delivered what may be the single most impactful framing for communicating this crisis to a general audience. The idea that we are replicating the conditions of the worst mass extinction in history is not hyperbole from activists. It comes from quantitative modeling published in one of the most rigorous scientific journals in the world. The institutional framework these researchers have assembled carries just as much weight as their individual contributions, because individual papers, no matter how brilliant, don't change policy on their own. Organizations do. Networks do. Sustained, coordinated, institutional effort does. GO2NE, the Global Ocean Oxygen Network, was established in 2016 under the UNESCO Intergovernmental Oceanographic Commission, a compact expert working group of 20 to 25 members drawn from institutions around the world. It has punched far above its weight in scientific output and policy influence. GO2NE produced the landmark 2018 science paper, helped organize the 2018 Kiel Conference, where more than 300 scientists from 33 countries gathered for the largest scientific meeting ever dedicated to ocean oxygen loss. And on September 7th, 2018, those attendees signed the Kiel Declaration on Ocean Deoxygenation, stating that the Paris Agreement and the 2030 Agenda for Sustainable Development are severely threatened by ocean deoxygenation. 300 scientists from 33 countries putting their names on a public declaration that this crisis threatens the foundations of international climate and development policy. That does not happen casually in science. GO2NE contributed extensively to the massive 2019 IUCN report and continues coordinating research and policy engagement under co-chairs Andreas Oschlies and Caroline Slomp. The Global Ocean Oxygen Decade, or GOOD, grew directly out of GO2NE's work and received endorsement as an official program of the United Nations Decade of Ocean Science for Sustainable Development, running from 2021 to 2030, with GOMAR as the lead institution. Its mandate covers building a sustained global ocean oxygen observing system capable of tracking changes in real time, improving scientific understanding of deoxygenation drivers and impacts through coordinated international research, and providing rigorous scientific guidance to policymakers at national and international levels. It marks the first time the international community has dedicated a full decade-long coordinated effort specifically to understanding and addressing ocean oxygen loss. The fact that such a program didn't exist until 2021 tells you something about how late the world came to recognizing the severity of this problem. The IUCN's December 2019 report, released at COP25 in Madrid, remains the most comprehensive single document on ocean deoxygenation ever produced, titled Ocean Deoxygenation. Everyone's Problem, it spans 588 pages across multiple chapters and draws on the expertise of 67 scientists from 51 institutions in 17 countries. Dan LaFolie, the IUCN's senior advisor on marine science and conservation, co-edited the report and delivered the message that has come to define its legacy. We are now seeing increasingly low levels of dissolved oxygen across large areas of the open ocean. This is perhaps the ultimate wake-up call from the uncontrolled experiment humanity is unleashing on the world's ocean as carbon emissions continue to increase. NOAA, the US National Oceanic and Atmospheric Administration, has anchored dead zone monitoring in American waters, funding annual Gulf of Mexico surveys, and operating the Coastal Hypoxia Research Program. The Mississippi River, Gulf of Mexico Watershed Nutrient Task Force, a state-federal partnership formed in 1997, set the target of shrinking the Gulf dead zone below 1,900 square miles by 2035, a goal that current trends suggest will not be met without dramatically accelerated action. HELCOM, the Baltic Marine Environment Protection Commission, adopted the Baltic Sea Action Plan in 2007 to coordinate nutrient reduction among the 9 nations bordering the sea. It remains the most comprehensive regional effort to address nutrient-driven deoxygenation in a shared body of water, and its mixed results, real progress on some fronts alongside persistent challenges on others, offer important lessons for similar efforts elsewhere. The UNESCO State of the Ocean Report 2024, launched in June 2024 inches, Iceland brought the latest data to an international audience, drawing on 98 experts from 25 countries. It reinforced the approximately 2% global oxygen decline and documented around 500 dead zones, reaffirming that the problem continues expanding. Taken together, these organizations represent decades of accumulated scientific expertise, monitoring capacity, and institutional infrastructure. They function as the machinery through which raw research becomes systematic monitoring. Monitoring becomes actionable data, and data becomes the policy recommendations governments need to make informed decisions. If any of them are defunded or dismantled, the world loses not just current monitoring capacity but irreplaceable institutional knowledge and long-term data records that make future action possible. You cannot rebuild a 40-year monitoring dataset. Once it breaks, it's gone. The picture so far has been almost relentlessly grim, and that's because the overall trajectory genuinely warrants alarm. But scientific integrity requires examining the areas of uncertainty, disagreement, and legitimate debate within the field. No scientific consensus is monolithic, and ocean deoxygenation is no exception. Start with what is not in dispute. No prominent scientist denies that ocean deoxygenation is occurring. The fundamental trend, approximately 2% oxygen loss since 1960, dramatic proliferation of dead zones, quadrupling of anoxic water volume, stands as well established and not seriously contested by anyone working in this area. But within that consensus, several important debates and areas of genuine uncertainty persist. The first concerns the relative weight of climate change versus nutrient pollution. In the open ocean, climate change clearly dominates. In coastal waters, nutrient pollution clearly drives the damage, with climate change acting as an amplifier. But the policy implications of that distinction matter. Some researchers and policymakers argue that nutrient reduction offers more immediate, actionable results within years or decades. Others insist that without simultaneously tackling global greenhouse gas emissions, local nutrient reduction will ultimately be overwhelmed by the warming-driven component. That tension plays out most visibly in places like Chesapeake Bay, where decades of nutrient management have produced real improvements, but where continued ocean warming threatens to reverse those gains over time. The second debate centers on the model observation mismatch. Earth system models reproduce only about a third of observed oxygen loss, and that is not a minor discrepancy. For most researchers, including Oshley's, the mismatch signals that the situation is likely worse than projections suggest, that the models are conservative rather than alarmist. But some scientists argue the gap reflects incomplete understanding of natural variability. Martin Visbeck at GeoMar noted in 2017, "With measurements alone, we cannot explain all the causes." Natural processes occurring on timescales of a few decades may also have contributed to the observed decrease. Some of the decline might belong to natural multi-decadal cycles the models don't capture. This is not climate denial. It is legitimate scientific caution about attributing every observed change to a single cause. But the weight of evidence strongly points to a human-driven component that is real, large, and growing. The third area of debate involves data quality and the limits of observation. A 2025 preprint on EGU-Sphere demonstrated that spatiotemporal gaps in ocean oxygen observations can amplify variability estimates by 150 to 500% and introduce 5 to 25% deviations in multi-decadal trend calculations. Historical measurements below 2,000 meters remain sparse, and different gap-filling methods produce somewhat varying results. The overall direction of the trend holds consistent across approaches, but the precise magnitude carries meaningful uncertainty bars. Some regions have actually seen oxygen increases over certain periods, driven by circulation shifts rather than any improvement in the underlying drivers. The ocean is not losing oxygen uniformly everywhere. It's a patchwork, with some areas declining dramatically and others holding steady or temporarily improving. The fourth and most consequential debate concerns reversibility. On the optimistic side, genuine success stories demonstrate that coastal dead zones can recover when the right actions are taken. The IUCN and other bodies have consistently emphasized that nutrient-driven coastal deoxygenation is, in principle, a solvable problem. Reduce the inputs, and the dead zones shrink. On the pessimistic side, the open ocean climate-driven component is essentially irreversible on any timescale that matters to human civilization. Even if all CO2 emissions stop today, the deep ocean will keep losing oxygen for centuries to a millennium or more. Less than 25% of committed loss has materialized. The rest is inevitable, locked in by heat. The ocean surface has already absorbed, but that hasn't yet penetrated to the deep. A 2016 Royal Society discussion meeting was notably cautious, concluding, "It is too early to say whether or not the socio-economic consequences are likely to be serious." That restraint reflected the genuine uncertainty of the mid-2010s. Since then, accumulated evidence has pushed the scientific community toward a considerably more urgent assessment. But the honest answer remains that nobody knows exactly how bad the downstream economic and social impacts will become, because they depend on policy choices that haven't been made yet. One more controversy deserves mention. In July 2024, a study published in Nature Geoscience by Andrew Sweetman and colleagues reported that polymetallic nodules on the deep ocean floor appear to produce oxygen in complete darkness. The nodules seem to function as natural geobatteries, generating enough voltage to split seawater molecules through electrolysis. If confirmed, this would represent a previously unknown source of deep ocean oxygen, but the finding is actively contested, with some scientists suggesting the oxygen readings may be instrument artifacts rather than genuine production. Follow-up expeditions are planned for 2026 to attempt replication. This is science in real time, messy and unresolved, and it would be irresponsible to present the finding as established fact. But it illustrates how much remains unknown about ocean oxygen dynamics and how surprises in both directions are still possible. Now for the success stories, because they exist and they carry enormous weight. The most striking accidental recovery happened in the Black Sea. Through the 1970s and 1980s, the Black Sea dead zone expanded catastrophically, growing from about 3,500 square kilometers in 1973 to approximately 40,000 square kilometers at its peak in the late 1980s. Agricultural intensification across the Soviet Union and Eastern Europe was pouring enormous quantities of fertilizer-derived nutrients into the Danube, Dnieper, and other rivers feeding the Black Sea, creating one of the worst cases of coastal deoxygenation anywhere on Earth, a vast expanse of water that could no longer support the fish and shellfish populations that Black Sea communities had depended on for centuries. And then something happened that no environmental policy could have achieved. The Soviet Union collapsed. The economic disruption following the dissolution of the USSR in 1991 carried a dramatic and entirely unintended environmental consequence. Fertilizer use across the former Soviet states and Eastern Bloc nations plummeted, not because governments mandated reductions or farmers adopted sustainable practices, but because the economic system that had subsidized and distributed industrial fertilizer simply ceased to exist. Farmers couldn't afford it, factories that produced it shut down or slashed production, and the centralized distribution networks fell apart. Practically overnight, nutrient runoff into the rivers feeding the Black Sea dropped sharply. The dead zone began to shrink, measurably, significantly, and faster than many scientists had thought possible. The ecosystem started recovering. Fish populations that had been displaced or decimated began returning, and the whole episode became an accidental experiment on a continental scale that proved conclusively reducing nutrient inputs could reverse coastal deoxygenation, even in a system degraded for decades. Nobody is suggesting economic collapse as environmental policy. The human suffering caused by the fall of the Soviet Union was immense. But the Black Sea case delivered irreplaceable proof of concept. The ocean can heal. Dead zones are not necessarily permanent, and the biology of recovery can outpace conservative scientific estimates, provided the root cause is actually addressed. Chesapeake Bay tells a more deliberate success story. The largest estuary in the United States has struggled with seasonal dead zones since at least the 1930s, driven by nutrient pollution from agriculture, urban runoff, and wastewater discharge from 6 states and the District of Columbia that make up its enormous watershed. Unlike the Black Sea, the Chesapeake's recovery has come through decades of intentional, coordinated, often politically contentious effort involving multiple levels of government, the agricultural industry, wastewater treatment facilities, and environmental organizations. Nutrient reduction programs targeting both nitrogen and phosphorus have operated for years through a combination of upgraded wastewater treatment plants, agricultural best management practices, stormwater controls, and regulatory enforcement. 6 watershed states and DC have now met 51% of their nitrogen reduction goals and 60% of their phosphorus reduction goals since 2009, representing billions of dollars of investment and decades of sustained political will. In 2023, Chesapeake Bay recorded its smallest dead zone since monitoring began in 1985, and its overall ecosystem health grade improved to a C+ for the first time in 20 years of assessment. For a body of water that had been declining through most of the 20th century, that C+ marks a genuine turning point, evidence that sustained, science-based intervention can reverse the trajectory of coastal deoxygenation. But the story doesn't follow a clean upward line. The years 2024 and 2025 return to near-average dead zone conditions, a reminder that recovery is not linear and that natural variability, particularly weather patterns controlling how much rainfall washes nutrients off the land in any given year, can temporarily mask or amplify the underlying trend. A wet spring means more runoff, more nutrients, and a bigger dead zone regardless of long-term improvements in nutrient management. Scientists also warn that continued ocean warming and changing precipitation patterns could eventually overwhelm the reductions, making it harder and harder to hold progress, even as human source inputs keep shrinking. The Chesapeake is winning the battle against nutrients, but it may be losing a slower war against warming. The Thames estuary in England provides the most dramatic long-arc recovery of all, carrying a powerful message about what becomes possible when a society decides that environmental destruction is no longer acceptable. In the 1950s, the Thames was declared biologically dead, and that wasn't a metaphor, it was a factual assessment. Centuries of unregulated industrial pollution, untreated sewage from one of the world's largest cities, and urban runoff from the sprawling London metropolitan area had turned the river and its estuary into an open sewer. Fish had completely disappeared from large stretches. The smell was notorious, a defining feature of riverside London that residents accepted as the price of industrial civilization. Nobody imagined the Thames would ever support life again. Today, through decades of sustained cleanup, massive investment in sewage treatment infrastructure, increasingly stringent pollution regulations, and a fundamental shift in how British society viewed its relationship with the river, the Thames has been transformed almost beyond recognition. The ZSL State of the Thames report from 2025 documents the return of diverse marine life to the estuary, including grey seals, seahorses, and more than 100 species of fish. Waters lifeless within living memory now support thriving ecosystems, making it one of the most remarkable environmental recovery stories of the past century. But a critical caveat runs through every single one of these success stories, and grasping it matters if we want an honest picture of where this crisis stands. Every recovery just discussed, the Black Sea, Chesapeake Bay, the Thames, reversed nutrient-driven coastal deoxygenation through nutrient reduction. They are victories against eutrophication, against the specific problem of excess fertilizer and sewage washing into coastal waters, and they prove this particular aspect of the crisis is solvable. Dead zones created by nutrient pollution can be reversed if the pollution drops. That finding should motivate urgent action on nutrient management worldwide. But the open ocean, climate-driven component has no equivalent solution. You cannot reduce nutrient runoff to fix warming-driven oxygen loss in the deep Pacific. You cannot upgrade a sewage treatment plant to reverse the expansion of the Arabian Sea oxygen minimum zone. You cannot pass a local ordinance to restore oxygen to water 1,200 meters below the surface of the North Atlantic. The only intervention that reaches climate-driven deoxygenation is reducing greenhouse gas emissions on a global scale. And even then, the oxygen already lost to warming will not return for centuries, possibly a millennium or more, even under the most optimistic emissions reduction scenario. This distinction between the reversibility of coastal dead zones and the multi-century irreversibility of open ocean oxygen loss may be the single most important takeaway from this entire video. The window for preventing the worst outcomes is not defined primarily by how fast we clean up nutrient pollution, though that absolutely matters and demands maximum urgency. The window is defined by how quickly we cut carbon dioxide and other greenhouse gas emissions. Every single year of delay locks in additional centuries of deep ocean oxygen loss that no cleanup effort, no policy intervention, no technological innovation, and no amount of money can undo after the fact. The deep ocean operates on timescales that make human political cycles look instantaneous, and once it has been set on a trajectory of oxygen loss, that trajectory plays out whether we are paying attention or not. Isabella Lövin, Sweden's Minister for Environment and Energy, articulated this at the launch of the IUCN report in December 2019. Whilst we have known about dead zones in the ocean for many decades, ocean warming is now expected to further amplify deoxygenation across great swaths of the ocean. We need to work together to get the ocean oxygen budget back in balance. Getting the ocean oxygen budget back in balance. It sounds like something reasonable people could agree to do. In practice, it requires nothing less than a fundamental transformation of the global energy system, the global agricultural system, and the global waste management system, all operating simultaneously, all sustained over decades against the resistance of entrenched economic interests that profit from the status quo. That is the scale of the challenge. And the ocean is not waiting for us to sort out our politics. Before we get to where things stand right now in 2025, it's worth tracing the full arc of how we got here, because the history of ocean deoxygenation is also the history of how long it takes for a slow-moving catastrophe to register in the human mind. That timeline explains why we are where we are today, and how narrow the remaining window for action has become. The story starts more than a century ago, in the 1910s. That's when scientists first documented what we would now recognize as dead zones, roughly 4 of them scattered around the world's coastlines. They were treated as local oddities, curiosities of particular harbors or estuaries where industrial waste or sewage had overwhelmed the water's capacity to sustain life. Nobody connected them to each other, nobody saw a pattern, and they remained footnotes in regional scientific literature. By the 1930s, the first dead zone turned up in the Chesapeake Bay, the largest estuary in the United States. Once again, it was treated as a local problem, a consequence of the rapid urbanization and industrialization rolling through the mid-Atlantic region. The idea that something similar might be happening globally, or that it might connect to the composition of the atmosphere, was simply not on anyone's radar. Through the 1950s, nutrient pollution from post-war agricultural intensification began driving hypoxia surges in the Baltic Sea. The Baltic, a shallow and semi-enclosed body of water surrounded by industrializing nations, was particularly vulnerable. But the Cold War split the nations around it, making coordinated monitoring and response practically impossible. The Baltic's oxygen was vanishing, and the geopolitical architecture of the era ensured that almost nobody could study it comprehensively. By the 1960s, the count of documented dead zones had climbed to about 45 worldwide. The Green Revolution was transforming global agriculture, dramatically boosting crop yields through massive application of synthetic nitrogen fertilizer. Food production soared, and so did nutrient runoff into the world's rivers and coastlines. Dead zones were multiplying, but scientists still understood them as isolated local pollution problems, not as symptoms of a systemic, planetary-scale process. A conceptual breakthrough arrived in 1976 that would prove important decades later. Schlanger and Jenkins, working with data from the Deep Sea Drilling Project, proposed the concept of oceanic anoxic events, or OAEs, periods in Earth's geological past when vast stretches of the ocean had gone oxygen-free. This marked the first formal scientific recognition that the ocean could lose its oxygen on a global scale, not just in polluted harbors but across entire ocean basins. At the time, it was considered ancient history, useful for understanding rocks and fossils but irrelevant to the modern ocean. That assumption would prove spectacularly wrong. In 1985, Nancy Rabelais began systematic annual measurements of the Gulf of Mexico dead zone. That decision, by a single researcher at a state university in Louisiana, would create the longest continuous monitoring record of any dead zone on Earth. A dataset spanning nearly 4 decades that remains indispensable for understanding how dead zones form, grow, and respond to changes in nutrient loading and climate. The scientific infrastructure we rely on today for understanding the Gulf dead zone exists in large part because one scientist decided to show up and measure the same stretch of ocean every summer for the rest of her career. By 1995, Robert Diaz and Rutger Rosenberg had compiled their first comprehensive global review, tallying 305 dead zones worldwide. The number was alarming, but the paper landed in a specialized journal and attracted limited attention outside the marine science community. The public remained almost entirely in the dark. In 1997, the Mississippi River, Gulf of Mexico Watershed Nutrient Task Force formed as a state-federal partnership, representing one of the first coordinated policy responses to a specific dead zone. A significant step, but its goals, including shrinking the Gulf dead zone below 1,900 square miles, would prove extraordinarily difficult to reach. And then came 2002 and the Oregon coast surprise. Dead zones appeared off Oregon for the first time in over 50 years of observation, driven not by nutrient pollution, but by climate-altered upwelling patterns. This was a conceptual turning point for the entire field. Up until that moment, dead zones were understood as a pollution problem. They happened where you dumped too much fertilizer or too much sewage. Oregon shattered that assumption. Dead zones could appear in places with no local nutrient problem whatsoever, caused by changes in deep ocean oxygen levels and atmospheric circulation patterns operating across thousands of miles. A farmer spreading nitrogen fertilizer in Iowa had nothing to do with the dead zone off the Oregon coast. That dead zone traced to the same global warming, melting Arctic ice and bleaching coral reefs on the other side of the planet. The problem could no longer be contained within the framework of local pollution management. It had gone unmistakably, undeniably global. By 2006, the Oregon coast reached true anoxia, zero dissolved oxygen, for the first time ever recorded in those waters. Underwater footage captured complete devastation. Ecosystems that had thrived for as long as anyone could remember, reduced to barren expanses of dead rock. That same year, the United Nations estimated roughly 200 dead zones globally, and the pace of discovery was accelerating, driven both by genuine proliferation of oxygen-depleted zones and by improved monitoring in previously unstudied regions. HELCOM adopted the Baltic Sea Action Plan in 2007, attempting to coordinate nutrient reduction across 9 nations. It was ambitious, politically complex, and a recognition that the Baltic's dead zones could not be addressed by any single country acting alone. On the 15th of August, 2008, Diaz and Rosenberg published their landmark science paper, documenting more than 400 dead zones, covering a combined area exceeding 245,000 square kilometers. The paper's central finding, that dead zones had spread exponentially since the 1960s, broke through to mainstream media for the first time. Ocean deoxygenation, or at least the coastal dead zone component of it, had finally reached public awareness, however briefly. That same year, Lothar Strama and colleagues published findings in Science showing that oxygen minimum zones in every tropical ocean basin were expanding. This was the open ocean counterpart to Diaz and Rosenberg's coastal findings, establishing that the problem extended far beyond coastlines into the deep interior of the world's oceans. In 2013, the International Programme on the State of the Ocean and the IUCN published their State of the Ocean report and introduced the concept of the deadly trio: warming, acidification, and deoxygenation. That framing proved critically important because it connected ocean deoxygenation to the broader climate crisis in terms non-specialists could grasp. It wasn't a separate problem, it was part of the same problem. Two important developments landed in 2016. GO2NE, the Global Ocean Oxygen Network, was established under UNESCO IOC, creating the first dedicated international coordination mechanism for ocean oxygen research. And Bristow and colleagues published their discovery in Nature Geoscience that the Bay of Bengal, bordered by more than 400 million people, harbored a massive dead zone at a tipping point of becoming fully anoxic. The crisis now had an institutional home and a deeply concerning new geographic frontier. On the 15th of February 2017, Schmidtko, Strammer, and Visbeck published their landmark Nature paper, providing the first comprehensive global quantification of ocean oxygen loss, approximately 2% since 1960. That single number, 2%, became the anchor statistic for every subsequent scientific paper, every policy discussion, and every news article about the crisis. Before Schmidtko's analysis, scientists knew the ocean was losing oxygen in various places, but lacked a defensible global number. After February 2017, they had one, and it was worse than many had expected. Lothar Strammer noted at the time, while the slight decrease of oxygen in the atmosphere is currently considered non-critical, the oxygen losses in the ocean can have far-reaching consequences because of the uneven distribution. Another grim milestone followed that summer. The largest Gulf of Mexico dead zone on record spread across 8,776 square miles of the Texas-Louisiana shelf, roughly the size of New Jersey, and brown shrimp habitat dropped by 25%. It was a visceral, economically devastating demonstration that despite decades of scientific awareness, task force formation, and policy discussion, the problem was getting worse rather than better. On the 5th of January 2018, the GO2NE team published their comprehensive review in Science, the Brightberg paper, documenting approximately 700 low-oxygen sites worldwide and the quadrupling of anoxic water volumes since the 1960s. No other paper had brought ocean deoxygenation to such a broad scientific audience. Later that year, Quest and colleagues confirmed the staggering scale of the Gulf of Oman dead zone at roughly 165,000 square kilometers, making it the largest oxygen minimum zone ever mapped in detail. In June 2018, Oshleys published his deeply unsettling finding in Nature Geoscience that computer models significantly underestimate observed oxygen loss, meaning the projections the world was relying on were almost certainly too conservative. And in September 2018, more than 300 scientists from 33 countries gathered in Kiel, Germany, for the largest conference ever dedicated exclusively to ocean deoxygenation. At its conclusion, they signed the Kiel Declaration, warning that the Paris Climate Agreement was severely threatened by the oxygen crisis unfolding beneath the waves. The following year, 2019, marked the moment ocean deoxygenation entered the top tier of international environmental policy discussion. On the 25th of September 2019, the IPCC released its special report on the ocean and cryosphere in a changing climate, projecting 3 to 4% ocean oxygen decline by 2100 under high emissions scenarios, and warning that oxygen loss would emerge over 59 to 80% of the ocean area within just a few decades. On the 7th of December 2019, the IUCN released its massive 588-page report at COP25 in Madrid, the most comprehensive document on ocean deoxygenation ever assembled by any organization, representing the work of 67 scientists from 51 institutions across 17 countries. The message left no room for ambiguity. The ocean was losing its oxygen, the consequences were already severe, and the world needed to act immediately. In 2021, the IPCC Sixth Assessment Report confirmed open ocean deoxygenation since the mid-20th century at high confidence. The Global Ocean Oxygen Decade launched as a UN program, and researchers identified 2021 as the year significant mesopelagic deoxygenation officially emerged from the noise of natural variability as a detectable, human-driven signal. IPCC AR6 Working Group 2 updated projections in 2022 to show subsurface oxygen losses of 4 to 11% by century's end. Penn and Deutsch connected our current trajectory to Permian-level extinction, and the EPA announced $60 million for the Gulf Hypoxia program, a significant but still inadequate investment. Chesapeake Bay recorded its smallest dead zone since monitoring began in 2023, delivering proof that nutrient management can work. July 2024 brought 3 major developments at once. Rose and colleagues proposed aquatic deoxygenation as a 10th planetary boundary in Nature Ecology and Evolution. The dark oxygen discovery was published in Nature Geoscience, and NOAA measured the Gulf of Mexico dead zone at 6,705 square miles. In September 2024, Go2NE hosted the first ever international workshop on marine reoxygenation in Paris. And that brings us to right now, to 2025, to where this crisis stands at this very moment. 2 contradictory realities define the current state of ocean deoxygenation research. The science has never been stronger, the institutional framework has never been more developed, and understanding of what needs to happen has never been clearer. At the same time, political and financial support for monitoring and action faces unprecedented threats at exactly the moment it is most needed. Start with the science. In 2024 and 2025, the Blender machine learning framework developed at Georgia Tech combined ship-based historical oxygen measurements with Argo float network data to produce the most detailed global reconstruction of ocean oxygen trends ever assembled. Its findings confirmed the approximately 0.7% per decade loss rate between 1970 and 2010 established by earlier studies. But a 2025 extension of the analysis uncovered something new and alarming. Severely accelerated oxygen loss in the Arctic Ocean and North Atlantic over the past decade, faster than any previous estimates had suggested. The cold, high-latitude oceans that have traditionally been the most oxygen-rich waters on Earth appear to be shedding that oxygen at an accelerating pace. Also, in 2025, the Gulf of Mexico dead zone measured approximately 4,402 square miles, below the long-term average. But as discussed earlier, the 5-year running average remains more than double the Hypoxia Task Force's 2035 target of less than 1,900 square miles. One below-average year does not signal a trend reversal. And a 2025 study from West Virginia University, Iowa State, and the University of Texas, funded by the National Science Foundation, calculated that actually achieving the EPA's 45% nitrogen reduction goal for the Gulf would cost approximately $7 billion per year. That number crystallizes the gap between what the science says and what the politics allows. We know what needs to be done and roughly what it would cost. Whether there is political will to spend it remains the open question. A fascinating nuance has also emerged from paleoclimate research. In January 2026, researchers at the University of Southampton published findings showing that the Arabian Sea was actually better oxygenated during a distant warm period when global temperatures ran warmer than today. The warmer climate produced more powerful monsoons, which drove stronger ocean circulation and delivered more oxygen to the deep Arabian Sea, offsetting the reduced gas solubility from higher temperatures. This finding does not undermine the overall deoxygenation narrative, but it reveals that the ocean's oxygen response to warming is more complex and regionally variable than simple models predict. In some regions, under some conditions, warming might actually boost oxygen delivery through enhanced circulation. The system is not as straightforward as warmer equals less oxygen everywhere, always. What is clear, however, is that the net global effect of current warming overwhelmingly drives oxygen loss. One of the most important and underreported stories of 2025 concerns the threat to the very monitoring infrastructure that makes all of this research possible. And that threat comes not from the ocean, but from the halls of government. The Trump administration has proposed cutting NOAA's research budget by 74%, from $485 million to just $171 million. Those proposed cuts would eliminate NOAA's Office of Oceanic and Atmospheric Research entirely, the very division responsible for funding and coordinating the scientific research underpinning our understanding of ocean oxygen dynamics. The National Ocean Service would lose 50% of its funding. If enacted, these cuts would directly threaten the annual Gulf of Mexico dead zone monitoring surveys that Nancy Rabale and her successors have maintained for nearly 4 decades, undermine the long-term oxygen measurement programs forming the backbone of trend analysis, and cripple the institutional capacity to detect new dead zones, track expanding ones, and provide the early warnings that coastal communities and fishing industries need to adapt. Senate pushback against these cuts has been real, and their ultimate fate, as of early 2026, remains uncertain. But the mere proposal exposes a structural vulnerability in our ability to track and respond to ocean deoxygenation that extends far beyond any single administration's budget decisions. Scientific monitoring of slow-moving environmental crises cannot be switched on and off like a light without consequence. It requires continuity. Nancy Rabelaise's Gulf monitoring program took nearly 4 decades to build. The historical oxygen measurement database Schmidtko drew on for his landmark 2017 nature study accumulated over more than 50 years from ships, buoys, and instruments deployed by researchers across dozens of nations. If these programs are interrupted for even a few years, the gap in the record cannot be filled retroactively. That data from the interruption years is simply lost forever, leaving a hole in our understanding at precisely the moment when trends are accelerating and the need for accurate, continuous information runs highest. This is not a partisan observation. It is a statement of physical and institutional reality. The ocean does not care which political party controls the federal budget. Dissolved oxygen will continue declining whether or not anyone measures it. The only question is whether we will know what is happening in time to make informed decisions about fisheries management, coastal infrastructure, public health, and economic planning, or whether we will be blindsided by consequences that could have been anticipated and mitigated had we simply maintained the ability to watch. In September 2024, GO2NE hosted something that had never been attempted: the first international workshop on marine reoxygenation held in Paris. The very existence of this workshop signals how serious the situation has become. Scientists gathered to evaluate whether it is possible to artificially restore oxygen to depleted ocean waters, essentially to give the ocean CPR, and whether pursuing such interventions was scientifically responsible or a dangerous distraction from addressing root causes. 2 main technological approaches came under scrutiny. The first involves direct air or oxygen injection, pumping atmospheric air or concentrated oxygen into hypoxic waters using compressors and diffuser systems installed on the seafloor or suspended in the water column. The technology is relatively straightforward and has been deployed in lakes and reservoirs for decades, essentially force-feeding oxygen into water that can't produce enough on its own. The second approach uses artificial downwelling, mechanical systems that push oxygen-rich surface water down into deeper, depleted layers, redistributing existing surface oxygen to where it's most needed, rather than adding external oxygen. Both approaches have shown measurable success in controlled environments, particularly in relatively small, contained bodies of water like lakes, reservoirs, and shallow estuaries. In those settings, oxygenation technology can demonstrably raise dissolved oxygen levels and improve conditions for fish, invertebrates, and the broader aquatic community. But the limitations become severe at ocean scale, and several of them may be fundamental rather than merely technical. The effects are temporary in every case studied. Oxygen levels drop immediately, sometimes within hours, when pumping or mixing operations stop. The underlying causes of oxygen depletion, whether nutrient loading from agricultural runoff or warming-driven stratification from greenhouse gas accumulation, go unaddressed by adding oxygen. You are treating a symptom while the disease keeps advancing. It is the environmental equivalent of giving a patient oxygen while their lungs continue filling with fluid. Useful in an emergency, but not a cure. Energy costs at anything approaching open ocean scale would be staggering. The Pacific Ocean's oxygen minimum zone alone covers millions of cubic kilometers, and the energy needed to meaningfully oxygenate even a small fraction of that volume would be enormous. In most realistic scenarios, that energy would come from fossil fuel combustion, generating the very carbon dioxide emissions, driving ocean deoxygenation in the first place. The mathematics of scale simply don't work unless the energy source itself runs zero carbon. And from an ecological standpoint, artificial reoxygenation can produce significant unintended consequences. Introducing oxygen into water that has been anoxic for extended periods disturbs the chemical equilibrium of the sediments below. Anoxic sediments accumulate methane, hydrogen sulfide, and other reduced compounds. When oxygen is suddenly reintroduced, it can trigger the release of trapped methane into the water column and from there into the atmosphere, where it acts as a greenhouse gas roughly 80 times more potent than carbon dioxide over a 20-year timescale. An intervention designed to help the ocean could end up accelerating the very climate change that created the problem. The intervention can also disrupt microbial communities and geochemical cycles that have adapted to low oxygen conditions, with cascading effects that remain difficult to predict and may prove difficult to reverse. The consensus from the Paris workshop was clear and sobering. Reoxygenation technology cannot substitute for reducing emissions and nutrient pollution. It may find limited, carefully targeted applications in specific critical habitats like coral reefs, fish spawning grounds, or aquaculture zones, where temporary oxygen supplementation could buy time while root causes are addressed. But it cannot solve the problem at the scale of the ocean. The water is too vast, the energy requirements too enormous, and the risks of unintended consequences too poorly understood for reoxygenation to serve as anything more than a niche tool in a much larger toolbox. One intriguing pilot project did emerge from the workshop discussions. In late 2024, a project called Box-In was announced, proposing to use excess oxygen generated as a byproduct of green hydrogen production to reoxygenate portions of the Baltic Sea. The concept works like this. Green hydrogen production uses renewable electricity to split water molecules into hydrogen and oxygen through electrolysis, and the hydrogen is the product while the oxygen is typically vented as waste. Box-In proposes capturing that waste oxygen and piping it into the Baltic's dead zones, turning an industrial byproduct into an environmental intervention. It pairs two urgent priorities: clean energy transition and ocean oxygen restoration, so each supports the other. Whether this approach will work at meaningful scale, and whether the oxygen delivered can overcome the Baltic's self-reinforcing phosphorus cycle, remains to be determined. But it represents the kind of creative, systems-level thinking this crisis desperately needs. In July 2024, a paper published in Nature, Ecology and Evolution introduced what may be the most consequential framing argument in recent ocean deoxygenation science. Rose and colleagues proposed that aquatic deoxygenation should be formally recognized as a 10th planetary boundary. The Planetary Boundaries Framework, originally developed by Johan Rockström and colleagues at the Stockholm Resilience Centre in 2009 and updated since, identifies the key Earth system processes regulating the stability and resilience of the planet's environment. 9 boundaries are currently recognized: including climate change, biodiversity loss, ocean acidification, freshwater use, and nitrogen and phosphorus biogeochemical cycles. Each boundary represents a threshold. Stay within it, and the Earth system remains in the relatively stable state within which human civilization developed and can continue operating safely. Cross it, and you enter a zone of increasing risk where large-scale, potentially irreversible environmental changes become increasingly likely. Rose and colleagues argued the accumulating evidence now supports adding aquatic deoxygenation to this list as a distinct, independent boundary. Their paper documented oxygen losses of approximately 2% in the global ocean, 5.5% in lakes, and a startling 18.6% in reservoirs since 1980. The crisis extends beyond saltwater. Freshwater ecosystems are losing oxygen even faster than the ocean, with potentially devastating consequences for drinking water supplies, freshwater fisheries, irrigation systems, and the aquatic ecosystems that hundreds of millions of people depend on. The proposal has generated debate, which is both healthy and expected. Lan Wang Erlandson of the Stockholm Resilience Centre, one of the architects of the existing framework, noted that some currently recognized boundaries, particularly climate change and the biogeochemical flows boundary covering nitrogen and phosphorus, may already indirectly capture the key dynamics of aquatic deoxygenation. Adding a 10th boundary could be seen as duplicating processes already accounted for, rather than identifying a genuinely independent Earth system process requiring separate tracking and policy attention. That debate carries real consequences. Whether deoxygenation wins formal recognition as an independent planetary boundary affects how the crisis gets prioritized in international policy discussions, how national science agencies allocate research funding, and how governments assess the completeness of their environmental commitments. If deoxygenation gets treated as a downstream consequence of climate change, subsumed within the broader warming narrative, it risks being pushed to secondary status, something policymakers assume will fix itself once emissions come under control. But that assumption ignores nutrient pollution entirely and underestimates how long the ocean will take to recover even under the most aggressive emissions scenarios. If deoxygenation wins recognition as an independent boundary, with its own metrics, its own thresholds, and its own policy demands, it forces attention on the full range of interventions needed, from agricultural reform to wastewater treatment to emissions reduction, rather than letting any single one be neglected. So where does this leave us? Let's bring the entire story together. We started this video with a simple statement: the ocean is running out of oxygen. Now you know exactly what that means, why it's happening, and what's at stake. Since 1960, the ocean has lost approximately 2% of its dissolved oxygen. 77 billion metric tons gone from the water, covering 71% of our planet's surface. Completely oxygen-free zones have quadrupled in volume. Coastal dead zones have exploded from 45 in the 1960s to roughly 700 today. Deep ocean oxygen minimum zones are expanding by millions of square kilometers, squeezing marine life into an ever thinner band of survivable habitat near the surface. And our best computer models account for only about a third of the loss we've measured, which means the real trajectory is almost certainly outrunning even the alarming projections we have. The economic toll already runs into billions annually. The Gulf of Mexico alone takes $2.4 billion in damage per year, according to the Union of Concerned Scientists. Baltic Sea cod stocks collapsed by more than 2/3 between 2010 and 2018. Tuna and billfish lost 15% of their habitat in the tropical Atlantic. A single jellyfish bloom cost South Korea $300 million. A single red tide wiped out 90% of Hong Kong's fish farm stock, a $40 million loss in one event. $42 billion of global tuna revenue faces the threat of shrinking oxygenated habitat, and more than 3 billion people worldwide who depend on the ocean for their primary source of protein are watching that protein source slowly suffocate. The geological record tells us, in terms that could not be clearer, what happens when the ocean loses its oxygen at scale. It has happened before. During the Permian-Triassic extinction, 81% of marine species were destroyed. The ocean became a toxic, hydrogen sulfide-producing death zone that poisoned marine life and land-based life alike. Recovery took an immense span of time. Princeton researchers have calculated that our current emissions trajectory points toward a comparable outcome by approximately the year 2300, and the Silurian extinction demonstrated that global anoxia isn't even necessary. 8% oxygen loss in the right places was enough to cause a mass die-off, severe enough to appear in the fossil record, a vast stretch of geological time later. Even if every nation on Earth stopped all carbon dioxide emissions tomorrow, the deep ocean would continue losing oxygen for 1,000 years or more. Less than a quarter of the committed loss has materialized. The remaining 3/4 are inevitable, an inheritance of warming that has already occurred and cannot be recalled, a debt the deep ocean will pay over centuries, whether or not anyone alive today is around to witness it. But the science also tells us, and this is the part that matters most, that recovery is possible. The Black Sea dead zone shrank dramatically when nutrient inputs dropped after the Soviet collapse. Chesapeake Bay recorded its smallest dead zone in nearly 4 decades, after decades of coordinated nutrient management. The Thames estuary, declared biologically dead within living memory, now supports grey seals, seahorses, and more than 100 species of fish. These recoveries are real, documented, and proof that when we stop damaging the ocean begins to heal. The scientists who have dedicated their careers to understanding this crisis, Denise Breitberg at the Smithsonian, Lisa Levin at Scripps, Andreas Oschlies at Geomar, Robert Diaz at the Virginia Institute of Marine Science, Nancy Rabelais in Louisiana, and dozens of others around the world, have built the knowledge base, the monitoring systems, and the institutional frameworks necessary to guide an effective global response. The research exists, the data exists, the understanding of both the problem and the solutions exists. What remains missing, the only thing remaining missing, is political will to act on what the science has been communicating with increasing clarity and increasing urgency for more than a decade. Denise Breitberg said it as simply and directly as it can be said. This is a problem we can solve. She is right. Nutrient-driven coastal dead zones can be reversed through better agricultural practices, improved wastewater treatment, and smarter land use planning. Climate-driven open ocean deoxygenation can be slowed, stabilized, and eventually stopped through aggressive greenhouse gas emissions reductions. These are not theoretical solutions awaiting some future breakthrough. They are proven, practical, and available right now, today. What they require is investment, sustained international coordination, and the willingness to prioritize the long-term health of the ocean over short-term economic convenience. The IUCN concluded its landmark 2019 report with words that have only grown more relevant with each passing year. What is reported here, and in the full technical report, is probably an underestimation of what is happening now. Science is incomplete, and broader awareness of ocean deoxygenation is just happening. But what is already known is very worrying. What is already known is very worrying. And what remains unknown may be worse. But worrying is not the same as hopeless. The ocean has survived mass die-offs before, and life has recovered from oxygen crises that dwarf the current situation. The question is not whether the ocean will eventually recover. Given enough time, measured in centuries or millennia, it will. The question is whether human civilization, with its fisheries, its coastal communities, its food security, and its billions of people who have no alternative source of protein, can afford to wait out the centuries or millennia that recovery will require if we do not change course now. Every breath you take, remember, at least half of the oxygen in it was produced by the ocean, by those microscopic phytoplankton we talked about at the beginning of this video, by Prochlorococcus, the tiny cyanobacterium that generates more oxygen than all the tropical rainforests on Earth combined. The same ocean that gives us the air we breathe is now quietly, steadily losing the oxygen that sustains the life within it. For 60 years, The ocean has been absorbing our excess heat, absorbing our carbon dioxide, and absorbing the consequences of our choices. It has been buffering us from the full impact of what we have done to the atmosphere, shielding us from warming that would otherwise have been even more severe. And it has been paying the price for that service in oxygen. The ocean is running out of breath, and whether it gets the chance to breathe again depends entirely on what we decide to do next.